So our transformer gives us a lot of candidate edges, right? And although we have only visualized 23 cells here, and so it's fine, feasible to visualize all edges when we have practical data sets with hundreds or thousands of cells. All of the edges might not be sensible as of yet, but we need to make a biologically sensible graph. For that, we need to enforce certain constraints. The first thing is that we only select edges where the probability is more than zero point 0.5. So it's more likely a realistic condition, something that the transformer predicts is actually an edge. Where we can also set the threshold as 0.99. The second is that we enforce that one parent per child, as in one cell cannot be formed from two previous cells in the previous time, right? 1 second ago there were two cells, suddenly they are one. A cell doesn't usually merge. So all of the accepted edges form a clean graph. We can also have some other conditions like normally cells will only have up to two children. So that can be another condition that we enforce. And so we create a valid division graph, as in one parent, maximum two children. And once all of the edges that remain satisfy these conditions, we get real graph edges, which means biologically sensible edges, or what likely represents a cell. Now, how would you select these edges? Because there are still a lot of edges, right, that might remain. So, one option is to select the greedy algorithm, which is a first come, first serve basis. The highest probability gets selected first, the second highest after that. But there is a much more feasible or better solution, which is global ILP, which uses linear programming to enforce certain global constraints, and it usually gives us a better optimal approach. Is generally preferred over the greedy approach. Now, when you apply this step over a lot of generations, as in this was just two time frames, right? But as more and more time frames come in, we can keep track of these edges and these nodes, and suddenly you have a graph. You can track a lineage. You do it two at a time, two temporal frames, but slowly and steadily you track a cell. And that's all that there is. You have dense image volumes that you give to these models, and they output a temporal lineage of a cell. You can track a cell, and it even tracks cell division events. So there you go. That's the entire pipeline.